Before I begin, I would first like to acknowledge that this session is intended for audiences that are highly skilled with Python and its related technologies, but also do not have a deep understanding of blockchain technology. Thus, I would like to take some time to explain some basic aspects of the Ethereum blockchain. If you are a blockchain expert, this session may not be suitable for you. Good afternoon. It's a great honor for me personally to be able to present at such a large conference like PyCon Korea and share my personal experiences to a large audience. Before I start, I would like to say thank you to everyone who had worked so hard to prepare and operate this conference for such a wonderful event. And I certainly hope everyone is enjoying the conference so far. All right, what I would like to talk about today is how Python can be used alongside with blockchain technologies, especially with the Ethereum blockchain. Now, for those who aren't familiar with blockchain, you might think, how exactly Python and the blockchain related with each other? I mean, there has been a lot of hype surrounding blockchain technology. I expect that's the reason why people chose to participate in this particular session. But Python on the blockchain, is that what the title said? Now, you might think of this strange relationship as something like this. Now, that statement definitely would look strange to most developers, let alone Python developers. However, that's actually not the case with this talk. If that was the case, this topic probably wouldn't have even been accepted as a talk with PyCon anyway. Actually, the relationship between the two technologies are pretty intimate. And I would like to explain how exactly Python and the blockchain can fall in love and how they can work together seamlessly. I would first like to start by listing some basic facts. The first one is that Python is a universal language that can run on almost every computer. Pretty basic, right? The second one may be new to some of you, that blockchain platforms can also act as a computer and be programmed like any other computer. If you weren't aware of this fact, you would find this last one surprising, that Python and some blockchain platforms share a similarly structured runtime architecture. Let me go into that. Most of you would probably have heard of Ethereum. Cryptocurrencies were what the Korean news was talking as a major issue just a few months ago, and now everyone knows what Bitcoin and Ethereum is. But actually, Ethereum isn't just a simple cryptocurrency, as some law enforcing authorities may think. It's a complete distributed computer that can run programs on them, just like a physical computer. And the execution engine behind all of that is called the Ethereum Virtual Machine, or the EVM. The EVM provides a lot of features for developers. First, it provides a Turing-complete execution environment. Sure, this may not be surprising, as most, if not all, computers are Turing-complete, but considering that this runs on a distributed network, it's a breakthrough for computer science. It also provides a high-level programming language called Solidity and easier code deployment support. They also feature adjustable code execution fees called gas in order to prevent malicious attackers from taking over the entire blockchain by taking up a large amount of compute power, because the EVM is both Turing-complete and open to everyone, since it's a distributed environment and without a single party to control it. Lastly, Ethereum also has better blockchain extensibility for actual application usage. Actually, Bitcoin can also run programs on its own through a system called Bitcoin script, but it was only designed to process Bitcoin transactions and not for general purpose applications. It does not have these features that Ethereum offers, and that's why Ethereum is often referred to as the second generation blockchain. Let me explain how all of this actually works. This is a simple Hello World program written in Solidity. There are literally hundreds of different ways to write a Hello World program with Solidity, but this one is one of the most simple implementations. Code targeting the EVM, like this piece of code, are also known as smart contracts because they were initially designed as contracts between multiple parties on the blockchain that automatically executes when certain conditions are met. Then, when we finish writing Solidity code, we then compile them in the form of EVM bytecode, which is the time of instruction the EVM can understand and execute on the blockchain. This is similar to Python and Java's approach of implementing a virtual machine with its own instruction sets to ensure platform compatibility. The compiled EVM bytecode is then deployed on the blockchain in the form of transactions and with its own address. I wouldn't go through too much on these processes because it would probably take an entire lecture course to fully explain this in detail, and most of you would probably be aware of this process, at least to some extent anyway. Finally, we can call and execute smart contracts already deployed on the blockchain from local applications called a smart contracts interaction library. Ethereum provides a library to access smart contracts locally called Web3, which allows developers to call smart contracts as if they were locally running code. We do require a value called an ABI, or Application Binary Interface, to correctly access the contract from the application. But modern smart contract development frameworks do most of the work for you, so that's less of a concern compared to what blockchain app developers had to deal with in the past. Now, all of these features sound very promising and revolutionary. The question is, why aren't blockchain-based app development or DApp development becoming widespread? To be clear, I also expected blockchain platforms to become the next app store just a few years ago, but they eventually failed to do so. Why? Well, from a technical perspective, it has poor development environment support. It does not even provide a proper IDE, excluding a web-based IDE from the Ethereum Foundation called Remix. Solidity's language syntax is confusing enough to prevent developers from joining the platform, and we cannot even choose a different language to develop for the EVM. It's also resource intensive because it's running code on a distributed system. Thus, it may not be suitable to participate in EVM code execution with distributed embedded systems like smartphones and IoT devices. This may be a huge problem, especially in the mobile-oriented contemporary society. Finally, the most important problem of all is that the EVM suffers from extensibility issues. The architecture simply isn't efficient enough to run high-quality and complex applications. If you try to do so, you need to pay a ton of gas for execution fees while still getting terrible performance. But as this isn't a problem that can be fixed within a short time, we will focus on these three things today, all of which can be partially solved with Python. Let me explain a little bit further on how Python can address these problems. First, I will give a brief overview on how we can integrate smart contracts with existing Python code and applications, and how to test them using PyTest. Next, I will show you how we manage to write and compile Ethereum smart contracts using pure Python, not Solidity. Finally, I would like to give you a sneak peek on modifying Python-based EVM implementations to be suitable for embedded systems. Let's start with the first one. These are some prerequisite software we used for this entire project: PyEVM, Trinity, Web3.py, and Populous. I won't go through them in much detail, but we will rely on the Populous framework to give you an idea of how Python-based smart contract development actually works. We first install and set up some required packages. I use Homebrew on macOS for easier package management since I am using a Mac. But if you are using Debian-based GNU Linux distributions that support APTs such as Ubuntu, the installation process should be pretty straightforward. This is the Hello World smart contract I showed you earlier. Even when we compile and deploy this code on the Ethereum blockchain, it cannot initiate an action in itself. We need additional code to control this contract. Let's add some Python code to control this smart contract then. The Python code on the right is used to test whether the smart contract was executed successfully using PyTest. Well, I know that this is an advanced session and that you guys all want to see some more complex and meaningful smart contract code like a voiding contract, token contract, or contracts for conducting ICOs, for example, but Solidity development is so complex that I simply cannot manage to explain them on stage for much detail under 40 minutes. I apologize for that. I will show you a Python version of one of them later on. Let's see how this simple Python code on the right controls the smart contract on the left. First, you might have noticed that the test hello world function here accepts a chain argument. This is actually a PyTest fixture. that is included with Populus's PyTest plugin. This chain object itself is provided by Populus, and this calls and creates a temporary test blockchain called tester. Once the test is complete, the tester blockchain is destroyed immediately from memory. To permanently deploy the contract on the test blockchain, we need to define a custom local blockchain that can be stored on permanent storage. Next, getting the get or deploy contract function creates a Web3 object that corresponds to the function with the name given. In this case, hello. This object isn't exactly the same as the contract itself on the left, but it does act as a wrapper that allows the developer to access the smart contract as if it was Python code. Then we call the sayHello function defined within the hello contract. Again, this isn't the real sayHello function. When we call this fake Python function, the Web3 Py library responds and calls the actual function for you. It even returns the value that the real function is supposed to return. In this case, hello world. Let's actually run the test then. For the time being, Populus has compatibility issues with newer versions of Ethereum-related packages and Python 3.7, so you may have to manually downgrade some packages and use an older version of Python depending on your setup. The Ethereum Foundation does not seem to be updating its Python packages as frequently as its JavaScript or Go packages, so I manually had to resolve some issues within the source code for these commands to work. I'm planning to make a pull request to resolve them, but the best solution for now is to downgrade your packages. If the compile was successful, you would see this message. The contracts.json file here stores the ABI, contract bytecode, and additional information Populus uses internally to access the smart contract. If you need more information or these information for other platforms, you can always manually extract them from this particular file. This command compiles and deploys the contract to the tester chain, which is the temporary blockchain used by Populus and PyTest. Because it is destroyed immediately after the parent process is killed, deploying to the tester chain is virtually meaningless. But developers often use this command to detect problems within the deployment process itself. Now it's testing time. As you can see here, it's the exact same PyTest experience you would expect from other Python projects such as Django. As the test succeeded, we know that our contract has successfully returned the result that we had expected. Hello world. At this point, that's interesting, but what about the new stuff that you promised, writing smart contracts themselves with Python instead of Solidity, and modifying the EVM implementation? We'll get to that in a moment. But before that, I would like to talk a little bit about my personal home IoT setup that I built using these solutions and how I started this entire project in the first place. This is my current home device setup: light controllers, coffee machines, curtains, and air conditioners, each paired to a Raspberry Pi, and all linked together using a private Ethereum-based custom blockchain network. There is a smart contract that automatically controls the behavior of each device, depending on weather condition or data from sensors attached almost everywhere. Having sensors attached all around the house makes me feel that I have my little own big brother, by the way. Not a real brother, but that big brother from 1984. Anyway, while building this project, I ran into a few problems. The first problem was that the Raspberry Pis were painfully slow to run the smart contract that I wished to run on it. They definitely had more than enough compute power to run the same code locally. What was the problem? Well, it turned out that I set the block mining difficulty to a level that the Raspberry Pis could not handle, thus significantly slowing down the blockchain's performance. Using a separate miner could have solved the problem, but I asked myself, would it be possible to optimize the blockchain and the EVM to a level that could be run on low-powered embedded devices? There's another problem that I had experienced. As you may have noticed, the Django controller server here, which enables manual control of each device through a web browser or smartphone app, is completely powered by Python. The Raspberry Pis that are directly attached to each home appliance for software-based control are also powered by Python. The question is, What about the smart contract itself? I mean, working with Solidity is definitely not a terrible experience, but wouldn't it be great if I could reuse at least some of the Python code that I had previously used with my Django server setup? Well, this may sound like a stupid question, but I figured out that it'll at least provide an in-depth insight on how general-purpose blockchains, including Ethereum, operate internally. Let's dive right in, shall we? This is a brief illustration of Ethereum's blockchain structure. It's pretty complex, especially compared to Bitcoin's, because it has been extended to accept general-purpose applications. There are some obvious similarities with the Bitcoin blockchain here, though, including this proof-of-work difficulty value, because current versions of Ethereum rely on mining for block generation and verification. Future versions of the Ethereum blockchain wouldn't rely completely on mining and proof-of-work, and they are already working to migrate to proof-of-stake-based protocols, which requires much less compute power to verify blocks. But today, we will only take a look at this part of the blockchain, especially on how exactly they handle code execution. This structure may be unfamiliar to some people who are used to the Bitcoin blockchain. The reason why it is structured like this is because Ethereum treats every transaction as a state transition. Bitcoin, on the other hand, relies on the UTXO model, or unspent transaction outputs, to make transactions, which basically views a transaction as a collection of multiple UTXOs as inputs. Ethereum, on the other hand, treats each transaction as an independent entity and even views code in this way as well, holding its own account. Thus, the state trie here is only storing information that has changed from the previous state. That's why it looks like this. There are a few features of the EVM that makes it similar to other execution environments. First up, the stack. The EVM does not provide the concept of registers, unlike physical microprocessors and some other virtual execution environments. A virtual stack is used instead for operations such as passing opcode parameters. There's also a unique feature of the EVM called the storage. This is a permanent key value storage mapping 256-bit to 256-bit words, memory space declared outside user-defined functions and within the contract context are stored in this area. Finally, there is, of course, the memory, which is, well, basically what you think of RAM, but only virtual. As all physical or virtual machines do, the EVM also implements a simple instruction set to make up EVM bytecode to ensure platform and ISA independence, which also applies to, yes, Python and Java as well. It also can be directly programmed at a low level with assembly language provided by Solidity. And it is also possible to use them side by side using the same contract. Finally, the EVM is theoretically language independent. The reason why it is theoretical is because due to its architectural limitations, that it is a distributed execution environment, the EVM cannot take full advantage of all features present in modern programming languages, such as Python. It also requires some unique language syntax because obviously the execution structure itself is quite different from previous implementations of virtual machines. But we'll try it out anyway because that's what I've always dreamed of. This is part of the Ethereum Yellow Paper, which is the document that defines the mathematical and technical specifications of the blockchain. As you can see here, the opcodes themselves look very similar to what we have already seen with Python's. Of course, the structure and definitions themselves are completely different, but it seems enough to make the two work together, at least to some extent. So again, will it be possible to develop a smart contract using Python? I made a list of the approaches that I could possibly take while trying to achieve this. I chose the third one, which was to allow Python code to compile directly to EVM bytecode without largely modifying or adding Python language syntax. Let me briefly explain why the first two were not considered appropriate. The first approach was to implement the Python interpreter itself as a smart contract in Solidity. This does seem viable at first because alternate implementations of Python like Jython in Java, or IronPython in .NET with a dynamic language runtime, or even PyPy written in Python itself work perfectly well and sometimes show even better performance than the standard C Python implementation, especially with PyPy. However, we need to consider that the EVM is not similar to any of these execution environments. The EVM is a distributed execution environment, which means it is currently severely limited in both features and performance. I could have done it if I wanted to, but it would have consumed an excessive amount of gas while still getting terrible performance. We could have also added EVM-specific syntax to Python as a superset of the Python language. You can think of it like Objective-C being a strict superset of C, but with added object-oriented programming capabilities with Smalltalk-style syntax. The Ethereum Foundation itself is working on a similar approach with a new experimental language targeting the EVM called Viper, which is not a strict superset of Python, but with very Pythonic syntax. This actually helps to protect the EVM against incorrectly written or malicious code, but this was not what we were exactly looking for in the first place. I mean, would a language with added syntax on top of Python still be called Python? Can we call Objective-C without the word objective? Can Viper be called as a variant of the Python language? I did not think so, and most of you will too. So back to our final approach. This is Solidity code that actually does something meaningful, as I promised earlier. It is a very simple implementation of a wallet that can be run on the Ethereum blockchain. When we deposit money from it, we add 1 to its balance. When we withdraw money from it, we deduct 1. We also throw exceptions when something goes wrong while depositing. Very simple, but has all the basic functions. The code on the right is the exact same code, but in Python instead of Solidity. The syntax here is still heavily work in progress, so don't tell me that it looks awful just yet, but at least it is now possible to at least partially run existing Python code on the Ethereum blockchain. Let's see how this actually works. This is how the standard C-Python implementation of Python looks like. We take the original Python source code, translate it into bytecode, and add some native library modules, and then run it on the Python virtual machine. But if we look closer, there are multiple steps to this translation process with largely 4 components: grammar, the lexer, the parser, and the compiler. The grammar component defines Python syntax. The lexer reads these syntax and turns them into smaller tokens. The parser creates a relationship between them, and the compiler finally translates them into Python bytecode. If you are an advanced Python developer, then you would probably be fully aware of this process. Also breaking down the translation process to find out what exactly has changed. We left the grammar component mostly unchanged, but slightly tweaked some of them to match their definitions within the EVM. The lexer have been modified to add tokens for EVM-specific features, the parser as well, to serve a similar purpose, and finally, we put components from the actual Solidity compiler source code to ensure compatibility. Because CPython and SolC were both written in C, it was relatively easy to integrate them, even though they were from entirely different projects. Now, back to the code. Let's look at how Python smart contract compares to its Solidity counterpart. First, the Ethereum module here is the warper that I mentioned earlier. It's a Python warper that allows EVM-specific features to be called within Python code. Next, the wallet class here inherits the contract class within the Ethereum module to create a contract. As contracts are not exactly the same as classes, we needed extra code to define some essential features of a contract compared to a normal class. The eth.mapping function returns an address access token to the mapping type value. A mapping is in Solidity and EVM can be seen as a hash table that maps every key to a value when initialized, but it's not quite similar to a hash table because the key values themselves aren't stored in the mapping itself. Only its CACAC256 hash is used to actually look up a certain value. Because such a type does not exist in Python, I just worked it with a function to ensure compatibility with existing Solidity code. The ETH.address type used within the mapping is a 20 type value, which is the same size as Ethereum's addresses. Thus, this code here means to create a mapping from the address size to an integer type that uses the address type value as a key when accessing the actual integer value. Finally, we also need to access mappings properly within Python code as well. We modified the syntax a bit so that it could also handle value access with mappings. Lastly, let's take a sneak peek at what has changed with the EVM over here for the embedded device network setup. First up, execution logic improvements. If a node has an embedded flag enabled, simultaneous code execution on that node switches off. That doesn't mean that the device will do nothing while all the other nodes are running smart contracts. Rather, each device only executes code that it requires to, and other nodes that aren't responsible for that code only checks its code hash and the execution results in order to ensure code integrity. In my case, for example, code that reads and analyzes sensor input would run on all nodes. But when a function that tells the light nodes to switch off is called from the main contract, that piece of code would only run on the Raspberry Pi that controls the lights. Next, bytecode optimization. Because embedded devices are able to partially choose which code that they need to execute, as I just mentioned, it is also possible to compile EVM bytecode ahead of time instead of just in time, if performance is absolutely important for you. AOT compilation occurs on multiple nodes simultaneously instead of just a single node. However, because we also need to check whether the compiled machine code was tampered with or not. You may have noticed that my descriptions on all of these technical changes are pretty vague, despite it involving some quite significant modifications to the architecture itself. One of the reasons for that is because they are only in their early stages of development and largely incomplete, because I am currently working on them as a little side project. But the most important factor is honestly because I only tested them under an extremely limited environment, only involving a few Raspberry Pis and home appliances. I decided that it was inappropriate to disclose the full technical details at this point. They may contain significant flaws with the architecture design that I was not able to test with other ISAs, devices, and larger network environments, and disclosing everything in detail could potentially mislead people into believing that this is the final design and code, even though this is very far from completion. But I do have one more thing to share. Now, while I was working on this entire project, I started to ask one fundamental question. Is the EVM efficient enough? I mean, both projects that I briefly covered today, building a Python compiler that targets the EVM and modifying the EVM itself, had a single purpose: to bring blockchain app development to more developers and allow them to take full advantage of blockchain technology. But the problem is the execution environment that Ethereum and the EVM provides is way too limited and too expensive to work around with. Maybe it's simply because the technology is still in its early stages and I am being way too pessimistic about it. Ethereum itself is definitely showing significant progress, with Ethereum 2.0 and other blockchains claiming that they achieved significant performance improvements are appearing as well. But solely from my development experience for all these platforms, from Bitcoin to Ethereum to EOS, they all suffer from the exact same problem that everyone is trying to solve: the extensibility issue. As the blockchain network increases in size, the cost for processing code increases significantly, and its processing performance decreases exponentially. As technology evolves, this dilemma is expected to be improved over time. But here's the real problem: who's going to develop on a platform with significant performance issues and limited features while having no significant advantage over cloud computing? Even cloud computing services are now going serverless. and they are much cheaper, have more features, and with much higher performance. These two EVM modifications that I've just mentioned, yes, they are not complete, yes, but they are also not complete solutions to the problems that I encountered while building my home network. Rather, these are workarounds specific for embedded devices to slightly improve their performance when the blockchain is under load. There are fundamental limits to this current design that prevents from running code efficiently enough. So I decided to merge all of these changes that I have personally made, including the Python EVM compiler and the modified EVM runtime covered today, to an entirely new distributed runtime project called Gemmer. It will be developed as an open source project on GitHub, not for commercial purposes, once the development work for both the compiler and the modified EVM has shown enough progress for other developers to make their own improvements and pull requests. Because a lot of optimization work is going on underneath, my first goal for this project is to put an entire custom Python implementation, yes, an entire Python interpreter running on a distributed runtime to fully embrace the power of Python for blockchain developers. The GitHub repo is not available just yet, but if you are interested, please stay tuned to my GitHub account for additional updates. I absolutely do not expect this to be the next Bitcoin or Ethereum or something, and I believe that this definitely has a very high chance of failure, but I definitely hope that these small projects and efforts combined, not just will be able to make a change with how people view blockchain technology these days, from simply a method to gain more cash with ICOs to a technology that is open to everyone and benefits everyone. Just like Python is the best language for machine learning because of its unique simplicity and played an important role in spreading machine learning technology to the masses, I also hope Python can also play a similar role in the blockchain world as well, with its simple and beautiful syntax being a powerful tool, also for blockchain developers. Thank you. If you have any questions, feel free to ask me afterwards or just email me at shchong@unifiededge.com. Enjoy the rest of the conference. Thank you.